Krause from University Federal di Santa Catarina, and he's going to speak about a prediction scheme for systems of partial differential equations with fast determining variables.
Thank you, Chairman. Thanks to the organizer, thanks Milton and Elena. Well, we consider is a model error in weather forecast. This is a big issue in weather forecast. You know that people in meteorology acknowledge that models are far from being exact in meteorology. And so many people in the field try to study how to deal with this issue, model error. One wishes to increase the predictability of weather events by means of reduction in the model error. Okay. To give you an example of how important is this issue, this is something I created myself when I was preparing a lecture for an ODE class. I wanted to show to the students some predictions, and I got those sample profiles of the evolution of precipitation at Florianópolis, which is an island in South Brazil, the onset of a cyclonic event. What you see here are three profiles, and they diverge considerably. Those are precipitation profiles. This is a 3.5 day forecast, and rain started about here, so they start capturing the event, the precipitation, but then this cyan model, which is the IMPA model, it's an American model, predicts huge rain concentrated in the day 2, say, I think this is day 2, while the other ones don't predict any rain at all, very small rain. And at the end, the IMPA model predicts no rain in day 3, while the other two, because there are two gray-like lines in here, they predict that the rain is going to start in May 26. Actually, what happened is that something in between, the precipitation started strong and then decreased a little bit. But so both are, I mean, this one starts correct, and then this one starts being correct. At the end, none of them is correct. This is might be seen as related to the Lyapunov instability, meaning stability to the initial value, but data simulation may be different for different models, so generating different initial values, but in general the initial values for those models should be quite similar, and so I guess the problem here is really model error. Okay, the models are simply different. They parameterize differently atmospheric physics, and so they provide different answers. Our proposal is to use a slight extension of Ladyssenskaya's concept of determining variables on the attractor. In Ladyssenskaya's theory, two different paths, two different trajectories with same values for the determining variables cannot coexist. And in this slight extension, we'd like to allow them two trajectories to coexist with same values of determining variables for a short while, for a short time. We shall call fast determining variables those determining variables, and the remaining variables we shall call the trailing variables. Some people might call these slaved variables. This is the scheme we propose. I think I should better draw instead of reading what's written in this slide. So the traditional picture of prediction goes this way. Here is time. This is Rn. We suppose we are going to be discretizing a partial differential equation into a system of ordinary differential equations. So this is the state space. And this is time 0. People use a cloud of particles. The particles are sample values of state. Presumably, one of those sample values is close to truth. So let's say truth is here, and one of those sample values is close to truth. What's done is, well, first, truth is going to evolve somehow, and you use an American model, US model, to evolve one of the sample values. A couple of UK models to evolve some other sample values, and so forth. So here maybe a Brazilian and a German model being used to evolve these initial states. I said, well, this is truth, okay, and someone is closer to truth. Let's say this one is closer to truth. This is going to the trajectory associated to this initial value is going to be called the control run, and this is what provides the prediction itself. The remaining particles are used to provide an estimate of the uncertainty of the confidence interval about the control run. So at every time you're interested in a prediction, you get here an estimate of the confidence interval about the average, and this is how this is the traditional picture of prediction schemes in meteorology. So the question is, if models are in error, what can you do? Which model are you going to use here to take over the control run? Well, if you are in Brazil, typically you use a Brazilian model to take over the control run. If you are in the US, you use an American model. So what we want to propose is the following. Where's truth? Truth is here. Okay, we also have a control run, but from time to time we do some analysis where we decide who's going to take over the time interval ahead of this analysis time, who's going to take over the control run, right? Maybe the UK model, then you repeat the analysis and you decide who's going to take over the control run for the next time interval ahead of this analysis time. Maybe you get the US model, and so forth. So maybe the Brazilian here. Okay. And how is this going to be performed? The idea is to, well, the other particles, they are advanced through the UK model, the US model, the Brazilian model, and at this first analysis time, you check the trailing value for each of these states and compare to the determining value in the control run. And those who are more compatible to the those states, those combinations were more compatible in the Lagrange theory, should be related to models that are more best fit, are more appropriate for taking over the control run ahead of this time. Okay, and this is what I'm describing here. Let me go to the derivation. So the derivation is based upon a splitted action formula, which some people call the Dyson formula in the physics community, I guess. And this is known for A and B, for operators A and B, which are transport operators. We take F as being the vector field, the ODE vector field, where the ODE here is the one that stems from discretization of the partial differential equation. And we take G as being this vector field with a fixed value of the tide variables. This decomposition of the state, of the vector state in two variables, here represents, X roof represents the trailing variables, and X tilde represents the determining variables. So we fix the determining variables and apply this formula with these vector fields. What we get is, with some approximation, is the following formula valid for a small time, for a short time. It's a short time discrete control formula, because the left-hand side says the following. This is a raw Blackwellization of a sampling of the roof variables, of the trailing variables. We are replacing the sampling of the tide variables by an estimate, presumably a sufficient statistic. And when you do this, you're doing something that is called a raw Blackwellization. But raw Blackwellization may provide, well, you prove through raw Blackwell's inequality that this provides a variance reduction of unbiased estimators of the expectation of the X roof variable by doing so. But this might not be a good algorithmic methodology for sampling phi roof, because you damage the statistics you know about X tilde. And in meteorology, you cannot damage the determining the statistics of the determining variables. So the right-hand side says you can do the same without damaging the statistics of the determining variables. You just need to perturb appropriately the initial value of X roof. And this is going to give you, at a later time t, a sampling of the roof variables which is equal to the sampling on the left-hand side. This is why this is a short-time discrete control formula. And the magnitude of the X, is what we are going to use to weight the UK, the Brazilian, the US, or BR models in those time intervals, at those analysis time. If the smaller the magnitude, the more compatible the states, the trailing and the determining states. Therefore, this gives the wave, and you choose the biggest wave to. So the cost is, the scheme adds a little cost to plain Monte Carlo sampling, and let's go to the results. We are going to use in this test study a moist convective rotating shallow water equation, which reads like this. the important thing is that truth is going to be drawn with time-dependent parameter values, while the scheme, both the traditional and the proposed scheme, are going to be run with constant values for these parameters. Those are the initial states. This is the trailing variable. The water depth is the trailing variable. So this is this initial truth, and this is the initial state for the control variable. And this is what we get after 48 hours. In the top panel is truth. In the middle is the proposed scheme result after 48 hours. And in the bottom panel is the traditional, the result under the traditional scheme. You see that the middle one captures pretty well truth at this time, while the traditional one doesn't capture, is already fading here at the top of the slide. That's it. Thank you very much.